So we want to find distance between distance from the line. Let's describe the line this way. Given by x equal to 3 plus 2t, y equal to -1 t, z equal to 4 minus 3t, to the point, let's call it S, and let's say it's 1, 3, 4. Okay, cool. You can memorize this formula. You can memorize this formula. I can't memorize this formula. For some reason, it doesn't want to stick. So I do think it's nice for these kinds of problems to really see what things look like, just because I find that to be the most useful. So if I'm thinking about this line, this point, well, great, here's my line. Here's the point that's not on it. And again, we're going to put any point on this line. And really the point we're going to pick is let t equal 0. You don't have to pick t equal to 0, but it's the easiest. If t is 0, then the point we're going to get is 3, -1, 4. So that's going to be this point on the line here. 3, -1, 4. We'll call that P. Here's the point S. It's 1, 3, 4. I happen to pick numbers that worked out similarly, but fine. And then we are trying to find this distance here, where you're essentially dropping a perpendicular from your point not on the line to the line. Call that D. This vector here from P to S, call the vector PS. And this angle between the vector PS and the line we'll call theta. Now I'll point out there's also a vector in the direction of this line, and it's really just the direction that the line is in. So we can draw some vector here. I'm going to call it V. And V is the vector that is the direction of the line, which is 2, 1, -3. So V can be the vector 2, 1, -3. And PS is just what you get when you start at P and end at S. So PS is going to be the vector 1 minus 3. So -2, 3 minus -1, and 4 minus 4. So those are all the things we need. Now we just have to think about what we're doing. I want to find that length. I'm going to use a trig function. It's either going to be sine or cosine. It's going to be, in this case, sine. So sine of theta is equal to the opposite length over the hypotenuse length. And then we do some math. I know since I've got sine, I want to make the cross product show up. So I'm going to multiply both sides by the magnitude of PS. I'm going to do it the smart way this time. So I've got that. And then I'm going to multiply the left-hand side also by the magnitude of V and divide by the magnitude of V. So doing it the weird way I did it last time. So what I'm going to have here is that D, the distance, is equal to the magnitude of PS times sine of theta. And then we're also going to multiply by the magnitude of V and divide by the magnitude of V. And the reason we are making these choices is so that then this left-hand side, the top part of it, is the magnitude of the cross product of V and PS. I'll just remind you, right, when you have two vectors, their cross product is equal to the magnitude of V times the magnitude of PS times sine of the angle between them times a unit vector n that's in the direction of the cross product. But if you're taking the magnitude of all that, the magnitude of the unit length thing doesn't matter. It's just going to be a contributing length of 1. So the magnitude of V cross PS is exactly what we've got in the numerator there. It's just the magnitude of V times the magnitude of PS times sine of theta. Cool. All right. So then we are going to calculate some stuff. Okay, so it's going to equal the magnitude of V cross PS divided by the magnitude of V. All right, so then this is where you actually have to use the dot product. Or sorry, the cross product, I apologize. So V cross PS, we're going to do the usual thing. there's a couple ways you can calculate this. I'm going to show you the way I like doing it every time because that's the way I like doing it. So you got your I, J, and your K. You've got your V, which is 2, 1, -3. And you've got your PS, which is -2, 4, 0. And then that's going to end up being I times. Now, I think after with practice, you can just do this in your head. Instead of writing the determinant of the 2 by 2 matrix 1, -3, 4, 0, I can just be like 1 times 0 is 0 minus -3 times 4, which is -12. So 0 minus -12. I think we can jump to that pretty easily. And then minus J times 2 times 0, which is 0, minus -3 times -2, which is 6. And then finally, plus K times 2 times 4, which is 8, minus 1 times -2, which is -2. So we end up getting the vector 12I plus 6J plus 10K. And then to calculate D here, it's going to be the magnitude of that. That's going to be the square root of 12 squared plus 6 squared plus 10 squared divided by the magnitude of V, which is the square root of 2 squared plus 1 squared plus -3 squared. And if for some crazy reason someone was asking me to do this on an exam, I would probably stop there and move on to something else. And if I had time at the end, maybe come back and simplify it. But really, you've demonstrated all the knowledge you need to demonstrate, in my opinion. Now, I know I'm not your professor, but I think this is enough. If you want to keep going, though, you get 144 plus 36 plus 100 all over the square root of 4 plus 1 plus 9. And that's something, I don't know, it's the square root of 280 over the square root of 14, which I guess kind of works out. I mean, okay, this one simplifies kind of nicely because 280 divided by 14 is just 20. So you could make this look really nice and say it's the square root of 20. That is the length of how far that point is from that line. Kind of cool. Nice when it works out nicely, but it doesn't actually matter. Okay. So now, so I should say, if you want, if you are able to, you can memorize this formula. You can say, oh, from a point to a line, it's just going to be the magnitude of the cross product of any point, any vector from a point on the line to the point off the line, crossed with the vector that's in the direction of the line, and then divided by the magnitude of that. I have a hard time remembering that. Yeah, but that's the formula. So let's talk about the other distance. Well, there's more than one, but the other main distance thing I think of is the distance from a point to a plane, which is going to be a little bit different, even though it feels kind of similar. So let's look at this next example. Also, if you all have questions, feel free to jump in. Let's say we want to find the distance from a point to a plane. Excuse me. So for example, we want to find the distance from the point, and it's pretty standard notation, at least in your textbook, to call the point that's not on the plane S. I don't know why they chose S, but they did. Let's say 2, 1, 6 to the plane given by 4x plus 6y plus 3z equal to 12. And what I would really quickly double check is make sure that point isn't on that plane. I mean, if it is, great, the distance is 0. If I plug in 2, 1, 6, I'm definitely not getting that equal to 12, so it's not a point on the plane. I'm going to draw a little picture. There's my plane, and here is my point S, not on the plane. 2, 1, 6. Okay, now here's where I often do the wrong thing, but I'm going to do the right thing. So I'm going to find some point in the plane. We always should be able to find a point. So if I'm going to try to make my life really easy, I'm going to pick the point 3, 0, 0. Or you could pick 0, 2, 0, or 0, 0, 4, or whatever floats your boat, as long as it satisfies this equation with the point in the plane. So I'm going to pick differently than what I've got over here. I'm going to pick the point to be 3, 0, 0. And we always want the vector from the point to the other point. So I'm going to write down PS over here, PS is just 2 minus 3, so -1, 1 minus 0, 6 minus 0. Or you can use the IJK, right? Notation, I don't care. You can use whatever you like. Obviously, we're going to go back. Obviously, I'm going between them all the time here, which is totally normal. Now, here's the thing we don't want to do. We don't want to drop a perpendicular from S to the plane. It's the wrong way to go. It's the way I usually end up going when I first do this every time. I'm like, oh, wait, this isn't working. What we actually want to do is we want to think about drawing a perpendicular from this point P upwards, and then thinking about the triangle it's going to make over here. So we want that right triangle. And our job is going to be to find that distance D. So we don't know what's going on with this length of the triangle here, and that's fine. We're going to use this hypotenuse of the triangle and this side that's adjacent to the angle that I'm about to draw, which is right there, theta. So now what we're going to say, instead of using sine of theta, we're going to use cosine of theta. So cosine of theta is equal to the adjacent side, which is D, divided by the hypotenuse length, which is the magnitude of PS. And then just like last time, instead of trying to get the cross product to show up, now we're going to try and get the dot product to show up because there's a cosine. So we're going to, again, multiply both sides by PS, or the magnitude of PS. And then we're going to multiply the left-hand side also by the magnitude of V divided by the magnitude of V. Oh, I should talk about what V is though, right? So what's V? Actually, I'm going to call it N, right? So yeah, V or N is the normal. So that vector right there is the normal vector. And so I want to multiply by the magnitude of the normal vector divided also by the magnitude of the normal vector. And then we're going to get that D is equal to, well, that top part there is just the dot product of N and PS. It's N dotted with PS. But since we want our answer to be a positive value, we're going to take the absolute value of that, because sometimes the dot product can be negative if the angle between the two things is greater than 90, divided by the magnitude of N. What is the normal vector here? You know it. You guys, you don't have to say it, but I know you know it. The normal vector here is 4, 6, 3. Or more generally, whenever you have a vector that's normal to a plane, the components are always just the coefficients of X, Y, and Z. Always works out that way. Kind of cool, actually. So here, if we want to find our distance, it's going to equal, well, let's see. I'm going to have 4, 6, 3 dotted with my PS, which is -1, 1, 6, divided by the magnitude of N, which is the square root of 4 squared plus 6 squared plus 3 squared. And then I guess I should put absolute values around this because maybe it's going to come out negative. So then we're going to get, let's see, 4 times -1 plus 6 times 1 plus 3 times 6 divided by square root of 16 plus 36 plus 9. And I dropped the absolute values because the top obviously is positive. So then you've got what? 20 divided by the square root of, I don't know, 50, 61. Yeah. And that is how you find the distance from a point to a plane. So here's the distance formula from a point to a plane. And there's the distance formula from a point to a line. Very kind of similar. You're always finding the vector from a point on your shape, on your thing, your line or your plane, to the point that's in space, not on your point or your line or your plane. And then you're either crossing it or dotting it, and then dividing it by the magnitude of the thing you're crossing or dotting it with. I have never been able to memorize these formulas. I've always just drawn it out every time. Now, it's not very efficient time-wise, but I do know that I'm doing the right thing once I've drawn it out. That said, if you have to do these, learn these things for your exam, you probably want to memorize them. Questions? Okay, more distances between things. I mean, distance between things is I don't know. I think it's interesting. It feels like you're actually doing a real thing as opposed to some of the more esoteric mathematical things. So we spend a little bit of time talking about it. Let's find the distance between skew lines. I will point out, if two lines are parallel, finding the distance between them is usually not too hard because you can basically just find their normal vectors. And well, I don't know. Well, I'll think about it now. Now that I've said it's easy, maybe we should do it. Let's do skew lines first. So let's say we have these two lines. L1 is given by x equal to 1 plus 2t, y equal to -3 plus 4t, z equal to -1 minus t. And L2 is given by x equal to 4 minus 2s, y equal to 1 plus 3s, and z equal to 2s. All right, so skew lines. Here's what I'm thinking. I've got two planes in which these skew lines live, and those planes are parallel to each other. There has to be, right? Two lines are skew. There's got to be a plane that contains each line that is parallel to the other plane that contains the other line. So here's maybe L1 in this plane here. And here's maybe L2 looking very not parallel in this plane here. And there's some point on both of those lines where we're going to find that distance between those 2 points. So I should make a comment here, right? Skew lines must exist in planes that are parallel to each other. That said, I'm not saying every plane that exists in is parallel to the other plane, just there has to be at least 2 planes that contain the skew lines that are parallel to each other. Okay, so I want to find the normal vector because usually that's helpful. And what we're going to do here, it's kind of tricky, but the vector that's normal to this plane is also normal to this plane. Right, because this vector is normal to both of the lines that are in those planes. Exactly what Patrick said. The normal vector is just going to equal the cross product of the vectors for each line. So the vector for line 1 is 2, 4, -1. And the vector for line 2 is -2, 3, 2. Kind of cool. So then we do the usual cross product thing. I, j, k, 2, 4, -1, -2, 3, 2. We get I times 8 minus 3. We get minus j times 4 minus 2. We get plus k times 6 minus 8. So we end up with 11i minus 2j, and then 6 minus 8. That's a 6, yeah, minus 8 is a plus 14k. Cool. So now what do we do? Well, we're going to place n on top of any point on our second plane here. But the way we're going to get a point on that plane is by picking a point on the line. So what's a point on line 2? I'm going to go easy again. For line 2, if I set s equal to 0, I'm going to get the point 4, 1, 0. So let's say we've got that.
So does the cross product always find the normal vector?
Well, so the cross product, if you take two vectors that are in a plane,
Yeah.
then yes, the cross product of those two vectors is going to be perpendicular to both of those vectors, which is going to shoot upwards out of it, or downwards if it's the other direction. But the idea here is that since these two vectors or lines have vectors that are parallel to it, sitting into those planes, you can essentially think of taking this vector here and moving it down into this plane here, and it would still sit in that plane. And so since that vector would sit in that plane, you can cross it with the vector for L2 and then get something that's going to be normal to this. Yeah, it's kind of a little tricky, but it totally works. So what we're going to do is we're going to take our point here, 4, 1, 0, and we're going to draw the normal vector coming out of it. And it's going to intersect the other planes, right? Right there. There's our normal vector. And then we're going to find some other point in this plane, because I don't know what point that this normal vector is actually going through. If I did, it'd be easy. I would just say, great, there's the distance I'm trying to find. But instead, we're going to pick some other point in this plane by picking some other point on line 1. Right, so again, right here is the point on L2. And here's the point on L1. But I don't know what that point is, so I'm going to pick some point here. And again, make the easy choice. It's going to be 1, -3, -1, just by setting t equal to 0. So that point there, let's call it S, is the point 1, -3. Sorry, 1, -3, -1. I feel like I said 0 before, which is incorrect. And this point here, P, is the point 4, 1, 0. And now I'm basically in the situation where I'm trying to find the distance from a point to a plane. So it's the same kind of idea as before, right? We've got this. We're trying to find that distance. We have this angle here, and it's the same idea. We can say that cosine of theta is equal to the distance we're trying to find divided by the magnitude of the vector from P to S. And then we multiply both sides by the same thing. So we're going to end up getting that D is equal to the magnitude of PS times the magnitude of the normal vector divided by the magnitude of the normal vector, all times cosine theta. But then that top part just ends up being the dot product. So here D is just the dot product of PS and N, an absolute value divided by the magnitude of N. So it's very much like you're finding the distance between a point and a plane. It's just before you could do that, you had to find the normal vector, and well, you had to find the normal vector. And finding the normal vector here was a little bit more work because we didn't actually have the equation of the plane. We just had the line that was in the plane. And so now, fun times, PS, so I need to write down what PS is. PS is, let's see, 1 minus 4, -3 minus 1, -1 minus 0. So PS dotted with N is going to be -3 times 11, -4 times -2, and -1 times 14. I do need the absolute values here because that is definitely a negative number, divided by the square root of, let's see, ooh, that's a kind of big, 11 squared plus -2 squared plus 14 squared. So that ended up being, let's see, -39 on top, so 39 over the square root of 121 plus 4 plus 196 is 321. Kind of gross number. You kind of get some gross numbers when you do these problems. It just, I mean, there's no avoiding it really. So the only difference between this thing we did now and the thing we did previously is before we were able to do the distance between a point and a plane, we had to find the normal vector to the plane, which was a little bit more work because we didn't just have the equation of the plane. Also, fun fact, I think it's fun fact. If we wanted to, you could totally find the equation of this plane now because you have a point in it and you have a normal vector to it. So just as a quick aside here, the plane containing the line L2 has the point 4, 1, 0, and the normal vector, where'd you go? 11, -2, 14. So if we wanted, we could find the equation. So its equation is 11x minus 2y plus 14z equal to some constant. And then we just plug in the point we have in the plane to find that constant. That's a d, not a 0. So we have 11 times 4 minus 2 times 1 plus 14 times 0 equal to d. So 44 minus 2, so d equals 42. So the equation of that lower plane is just 11x minus 2y plus 14z equals 42. And in a similar way, you can find the equation of the other plane, it would just be a different constant because they're parallel planes, so they have to have the same coefficients. Right, and the way you find the other number is you would say, well, I have 11x minus 2y plus 14z equal to some other number. Let's call it e because I already used d, and then you would plug in the point s you had from the other plane. So then we're going to plug in 1, -3, -1, and we'll get 11 plus 6 minus 14 equal to e. So e equals 3. So then the equation of that would be 11x minus 2y plus 14z equal to 3. Sorry. So I said a thing a little bit ago, kind of offhandedly, and it feels like it should be true, but I'm curious about how true it is. So I said, maybe incorrectly, finding the distance between parallel lines seems like it should be really easy. Let's think about this though for a second. So let's say we have these two lines. So let's say we have line 1 given by x equal to 1 plus 2t, y equal to 3 minus 4t, z equal to 6 plus t. And then in a similar way, L2, we're going to have x equal to 5 plus 2s, y equal to 1 minus 4s, and z equal to 2 plus s. These lines are clearly parallel. As the vector for the first line is just 2, -4, 1. And the vector for the second line is a multiple that it actually happens to be the same, but they could have been multiples and that also would have worked out just fine. So the question then is there an easy way to find the distance between these two lines? I don't actually know. Like I don't have a plan here. I'm really just curious because it seems like it should be an easy question to answer. I don't actually know. Yeah. Interesting. I'm really kind of like, how would you find them? I don't know. Let's think about it. So we've got these two lines. I think it's going to be finding the distance between the line and the point. That's how I'm imagining it here. Let's kind of think about it. So here's our two lines. Here's L1, L2. And yeah, I feel like this is good. So let's see. So on L1, let's pick a point. Sorry, on L, let's pick a point on L2 and a point on L1. We'll do it for both. So here's a point on L2. So on L2, I'm going to get 5, 1, 2. So when s equals 0, I get 5, 1, 2. And on L1, I pick t equal to 0, I'm going to get 1, 3, 6. And so I'm trying to find that distance there. And so I'm going to, again, draw this vector here. And then I'm going to call this P, this S. I'm trying to find this distance D. It's going to be a cross product situation. So let's see what happens. So we're going to say that sine, right? Even though I know what the formula is at this point, like I could actually tell you what it is, I still want to write it out starting with sine of theta because it just feels more natural to me. You don't have to do this, but I do think it helps develop the understanding of what's happening. So do what you want. So sine of theta is d divided by the magnitude of PS. And then we know that d is going to equal the magnitude of PS times the magnitude of the vector v, where v is just the 2, -4, 1, which you can't see up there. So magnitude of PS times the magnitude of v divided by the magnitude of v times cosine of theta. That's exactly going to equal the absolute value, sorry, the magnitude of the cross product of PS and v divided by the magnitude of v. I'm really curious to what's going to happen. Oh, you know what? Interesting. No, that's not a little bit. Yeah, I want to say you could just like find a normal vector, but I don't think that's really true. So let's see what happens here. So that's going to be PS cross v is going to equal, see, I got an I, J, and K. PS is going to be 1 minus 5, 3 minus 1, 6 minus 2, and V is -2, -4, 1. Let's be extra careful with our calculations here. We're going to get an I times 2 minus -16. We're going to do minus J times -4 minus 8. And we're going to do K times 16 minus 4. So that's going to end up being 18I plus 12J plus 12K. Doesn't seem particularly interesting, but all right. So then calculating D is going to be the magnitude of that. It's going to be the square root of 18 squared plus 12 squared plus 12 squared divided by the magnitude of V, which is the square root of 2 squared plus -4 squared plus plus 1 squared. Doesn't seem particularly interesting, but let's go through the motions just to figure out what we've got here, because maybe there's something interesting at the end. Let's see. So 18 squared is what? 324. I think. Yeah, that seems right. It was 144. It's 144 divided by the square root of 4 plus 16 plus 1. It doesn't seem particularly nice. I don't think. Like, I don't see anything here, but let's go ahead and I guess we should actually calculate the thing just because maybe there's something here. Let me double check my math. Just want to be sure about things. Yep. All right. No, it's not at all nice. So we end up getting square root of 612 divided by the square root of 21, which at least to me doesn't seem immediately like you could have looked at the parallel lines and seen that from the get-go. Maybe I'm not seeing something special here, but I'm gonna do some more investigation later on because I'm curious now. But as far as I know, it doesn't seem particularly easy to find the distance between parallel lines. So it's not any easier than the distance between a line and a point in general. Right, exactly. Yeah. And like it feels like we should be able to somehow identify the points that are like here and here, but not really. I wish that were to be true. I don't think it's actually true. Yeah. I remember there being a problem in 21C last quarter about like finding the distance between two skew lines and how it's the distance or the minimum distance between two skew lines is always just the length of the what's it looking for? The communal perpendicular line. Like there is no other communal perpendicular line. There is one, and it connects the 2 points that are closest to each other, which is kind of neat. It was a weird problem. I remember being from someone's class that was challenging. All right, more physical things, just because I think they're neat. Yeah, we got time. I mean, not just because I think they're neat, because they're in the text. You were supposed to like have seen them. So we'll get through these examples and then we'll move along. We want to find the angle between two planes. Planes x plus 2y plus 3z equal to 6, and we'll call that plane 1. And x minus 2y plus 4z equal to 8, which we'll call plane 2. So let's draw a picture here. Give myself some space to work with before I screw things up here. Give me a moment. Give me a moment to draw this picture here because I often kind of screw it up. Yeah. Cool. So here are my 2 planes. We are trying to find the angle between them. Which angle? That's a good question. Am I trying to find this larger obtuse angle or this smaller acute angle? I'm sorry, let's call that theta 2, not theta 1. And the answer really is whatever they ask for. So they should tell you that they want the acute angle, typically is what they will ask for. So find the angle between 2 planes. All we really have to do is find the angle between their 2 normal vectors. So this plane here has a normal vector. Draw this in a way that's going to make it hard to see the normal vector. Let's draw it that way. There's my normal vector for plane 1. Let's call that N1. And here's my normal vector for plane 2. So here's plane 1, here's plane 2. And then the angle between those vectors is exactly the same as the angle between the planes. So this angle here is the same as theta 2. So it's actually really not terrible at all. We just want to find the angle between N1, which is the vector 1, 2, 3, and N2, which is the vector 1, -2, 4. Again, those normal vectors just pop right out because they're just the coefficients of the planes, of x, y, and z in the planes. So in the angle between 2 vectors, I know it's been a little while since we've done it, but it's just going to be cosine of the angle is equal to the dot product of your vectors divided by the magnitude of those vectors. So here we're going to get 1 times 1, 2 times -2, 3 times 4, divided by the magnitude of N1, which is the square root of 1 squared plus 2 squared plus 3 squared. And the magnitude of N2, which is the square root of 1 squared plus -2 squared plus 4 squared. So we end up getting that cosine of theta is equal to, let's see, 12 minus 4 is 8 plus 1 is 9 over the square root of 14 times 21. That means our angle is going to be the inverse cosine of 9 over the square root of 14 times the square root of 21. And then you can either leave your answer. So here's what I will say about this. If you're answering this like in web work, you're probably going to leave your answer like this. Now, if they want both angles, you're going to do this angle and then I minus this angle. So I should ask you both a question, or all of you actually on Zoom as well. Is this angle I found right here, is that angle acute or obtuse? No, not necessarily. No, not 1 or 4. So inverse cosine spits out angles between quadrants 1 and 2. You're thinking of inverse sine and inverse tangent. Unfortunately, they're not all the same, which is kind of dumb. Well, it's not kind of dumb. It totally works really good. But inverse cosine spits out angles between quadrant 1 and quadrant 2. So you can get acute or obtuse angles. The only kind of deciding factor is, are you taking the inverse cosine of something positive or something negative? And here we're taking the inverse cosine of something positive. So we're definitely having an acute angle because cosine of an angle in quadrant 1 gives you a positive value. whereas cosine of angle in quadrant 2 would give you a negative value. So based on the sign of this, we know that this angle must be acute. Because what we're really saying is cosine of theta equals a positive number. For cosine to equal a positive number, the angle had to have been in quadrant 1. If you're limiting yourself to being between 0 and 180 degrees. Kind of neat. Right. The sign, well, and the sign isn't really an option here because you're definitely stuck using the dot product. That's why it's, yeah, the whole kind of thing where you're right. You sign is not the way to go if you're trying to find the angle between things, or because it really doesn't give you all the options you want. So our smaller angle, which I've labeled as theta 2, would be the inverse cosine of 9 over the square root of 14 and the square root of 21, which if you plug that into a calculator is approximately 58.3 degrees or 1.018 radians. And then the other angle, theta 1, I would just say is approximately 180 degrees minus 58.3 degrees, or approximately pi minus 1.018 radians. Continuing with this example, what about the line of intersection between those two planes? Well, we've got some normal vectors, and both of those vectors that are normal to those planes are also normal to the line that is contained by those planes. So if I want to say find I want to find the angle, sorry, the line of intersection between the same planes. X plus 2y plus 3z equal to 6, and x minus 2y plus 4z equal to 8. We're going to take the normal vectors. So n1 is still 1, 2, 3. N2 is still 1, -2, 4. We're going to take their cross product, and their cross product will give us the direction of the line. Now, that's not enough, but it's getting there. So N1 cross N2 is going to be all right, usual thing. IJ it up. 1, 2, 3, 1, -2, 4. Just to switch it up, let's do it the other way. Just for people who are fans of doing it the other way. You can do the thing where you do the I1, 1, J2, -2. So then we're going to get this is equal to that times multiplied, that multiplied, that multiplied. So we're going to get 8i plus 3j plus -2k, and then minus the other direction. It's going to be k times 2, I times -6, and j times 4. So altogether, that's going to give us 8i plus 6i, 3j minus 4j, and -2k minus 2k is -4k. So this line, that's the intersection of, so right, we're talking about, just so you can see it, you kind of see that, right? Yeah. We're talking about this line right here. So we've got the direction of the line. Now we need a point on the line. How do you find the point on the line? The intersection of these two planes. So here's how you do it. To find the point on the line of intersection, let any one of those three things be 0. Now I'll point out, this doesn't always 100% work the first time. So let either x equals 0 or y equals 0 or z equals 0. And then solve for what's left behind. So here's what I mean. So I'm going to pick x equal to 0. So if I let x equal to 0, then we're left with 2y plus 3z equal to 6 for plane 1. And negative 2y plus 4z equal to 8 for plane 2. And then I'm going to solve for y, and z here. So if I do that, I'm going to get, let's see, I'm going to isolate 2y and say 2y equals 6 minus 3z. And I'm just going to plug that in for the 2y right there. So I'm going to have negative 6 minus 3z plus 4z equal to 8. So negative 6 plus 3z plus 4z equals 8. So 7z equals 14. So z equals 2, which means y equals 6 minus 6. So 2y equals 6 minus 6. So I happen to also get y equal to 0. That's kind of atypical, but fine. So that means a point that's on this line is x equals 0 and y equals 0 and z equals 2. So our point is 0, 0, 2. Now, if you made a different choice, like if you started with z equal to 0, you would get x equal to something else and y equal to something else. Here's the thing about this method. Sometimes it doesn't work the first time because maybe your line happens to be parallel to the xy plane. And so if you pick z equal to 0, you're not going to get a point where that line intersects the xy plane. But a line can only be parallel to one plane at most. So, well, I mean, one of the 3 coordinate planes at most. So once you've eliminated one possibility, like you pick z equal to 0 that didn't work out, then either picking x equal to 0 or y equal to 0 will be totally okay. So then finally, and we'll wrap this up here, to write the equation of the line, the equation is just going to be, I'm going to write kind of the short way, it's your point, 0, 0, 2, plus your variable t times your vector, and your vector was 14, negative 1, 4. You write it like, and that we usually call that R of t. That's the equation of your line. You can also write it using the parametric equations like x1 equals 0 plus 14t and y equals 0 plus negative t and z equals 2 plus 4t. But this is the way we're going to start doing things in the next chapter. You're very welcome. All right, that's all I've got for today. Enjoy the weekend. Check out Whole Earth Festival. It's a fun time usually. So yeah. Take care.